16 days ago, a magnitude 7.5 earthquake struck the Tonga Trench. The aftershocks never came. Instead, something worse happened. The energy started moving south, toward New Zealand. And while that stress was migrating along one of the fastest collision boundaries on Earth, a fault on the other side of the Pacific, one that has not broken in 326 years, just recorded 791 tremor events in a single day. 2 megathrust systems. Same warning sign, same week. Tonight I am going to show you what this means and why seismologists are losing sleep over it. Stay with me. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as this story unfolds. Drop a comment with where you are tuning in from, what time it is there, and tell me this. 2 megathrust faults on opposite sides of the Pacific just started showing the same warning sign in the same week. One is migrating toward New Zealand, and the other has not ruptured in 326 years. So what happens when both systems are loading at the same time, and nobody can tell you whether it means something or not? Let me know your thoughts in the comments. Now, let us get into it. Part 1. 16 days ago, the floor of the Pacific Ocean broke. Not in some quiet, forgettable way. Not in a small tremor that rattles a coffee cup and vanishes from memory before lunch. This was a magnitude 7.5 earthquake, more than 30 kilometers beneath the Tonga segment of the Kermadec Trench, one of the most violent collision boundaries on the face of this planet. The kind of event that, under normal circumstances, would generate its own aftershock cloud, radiate energy outward like ripples in a pond, and then slowly, predictably fade according to a statistical law that seismologists have trusted for over a century. That is not what happened. What happened instead is something that should make you pay attention, because as of right now, 2 of the most dangerous subduction fault systems on Earth are showing the same category of warning sign at the same time on opposite sides of the Pacific Ocean. And unless you understand what that actually means in mechanical terms, you're going to miss why the people who study these systems for a living are quietly watching their screens a little more carefully than usual. Let me show you what is going on. The Tonga earthquake struck on March 24th, 2025. It was a significant event by any standard. A 7.5 on the moment magnitude scale releases energy roughly equivalent to 32 million tons of TNT. That is not subtle. That is not a tremor you debate over coffee. That is a boundary rupture on one of the fastest converging plate margins anywhere on Earth, where the Pacific plate is diving beneath the Australian plate at rates approaching 7 to 9 centimeters per year. To put that in perspective, your fingernails grow at about 3 to 4 centimeters per year. This plate boundary is moving almost twice that speed, grinding, compressing, and storing elastic energy along a fault corridor that stretches more than 1,000 kilometers from Tonga in the north to New Zealand in the south. Every single year, that boundary swallows another few centimeters of Pacific plate beneath the Australian plate, and every single year the elastic strain stored along that interface increases. The plates do not slide smoothly, they lock, they stick, and the energy that would have been released by continuous sliding gets banked instead, stored in the rock like tension in a coiled spring, waiting for the moment when friction can no longer hold. When a magnitude 7.5 ruptures a segment of that corridor, the textbook expectation is clear. You get a burst of aftershocks, concentrated around the rupture zone, decaying in frequency over time according to what is called the Omori law. Named after the Japanese seismologist Fusakichi Omori in 1894, it is one of the most reliable empirical relationships in all of seismology. Big earthquake happens, aftershocks follow. They cluster near the rupture. They get smaller and less frequent as days pass. The system relaxes, energy dissipates, things calm down. It is one of the few things in earthquake science that behaves almost like clockwork, and seismologists have been using it to model aftershock behaviour for over 130 years with remarkable consistency. Except this time, the aftershock sequence did something strange. The initial burst was muted, unusually quiet for a 7.5. The dense cloud of smaller earthquakes you would expect to see concentrated around the rupture zone simply did not materialise on schedule. It was as though the energy that should have been released locally had gone somewhere else, as though the system had absorbed a massive rupture, and instead of exhaling in the normal way, it had held its breath. And if you are a seismologist staring at a monitoring screen and the energy from a major earthquake appears to be missing from the expected location, there is really only one question that matters. Where did it go? Because the energy did not vanish. That is not how physics works. You do not pump 32 million tons of TNT equivalent into a fault system and have it simply disappear. The rupture released energy. The plates displaced. The stress field around the rupture zone was rearranged. But the expected local expression of that rearrangement, the dense aftershock cloud, the predictable decay, did not show up where it was supposed to, which means it showed up somewhere else. The answer started to appear several days later, and it appeared to the south. This is the part that changes the story from a single earthquake event into something that demands a different kind of attention. Because what the monitoring networks began to pick up was not a typical aftershock cloud radiating outward from the Tonga rupture. It was not the omnidirectional scatter pattern you see when a fault breaks and the surrounding crust adjusts uniformly in every direction. It was a linear progression, a stepping pattern. Multiple magnitude 5 and above events appearing progressively farther south along the Kermadec Trench, aligned along the strike of the fault, marching in one direction with a consistency that does not match random aftershock behaviour. Each event farther south than the last. Each event separated by days, not hours. Each event sitting on the same structural corridor, following the same fault geometry, as though the stress from the original 7.5 was being passed along the system like a baton in a relay race. They were heading toward the Hikurangi subduction zone. Now I need you to understand what this pattern means in mechanical terms, because it is the difference between a story about one earthquake and a story about an entire fault system waking up. When aftershocks cluster around a rupture, that is local energy release. The fault broke, the surrounding rock adjusted, stress was relieved. That is normal. That is relaxation. It is the geological equivalent of a pressure valve opening. The system vents, the tension drops, and equilibrium is gradually restored. But when seismicity migrates along the strike of a fault in a directional pattern, that is not relaxation. That is redistribution. The stress did not vanish, it transferred. It moved along structural weaknesses in the fault system like a pulse travelling through a wire, and each new event along that migration path represents the next segment of rock, adjusting to the new stress state created by the event before it. The system is not venting, it is rearranging, and rearrangement means that somewhere along the line, a segment that was previously stable is now closer to failure than it was before the Tonga earthquake happened. This is called Coulomb stress transfer, and it is one of the most important concepts in understanding how fault systems communicate internally. When a large earthquake ruptures one segment of a fault, it changes the stress field on adjacent segments. Some areas are brought closer to failure, others are pushed farther from it. The pattern depends on the geometry of the fault, the orientation of the slip, and the mechanical properties of the rock. But the critical takeaway is this: stress does not disappear when an earthquake occurs. It rearranges. It shifts from one part of the system to another. The total energy budget of the fault system changes, and the distribution of where that energy is concentrated changes with it. And in a system as long and as continuous as the Tonga to Kermadec to Hikurangi corridor, that rearrangement can propagate over enormous distances, hundreds of kilometres, potentially farther, segment by segment, patch by patch, like a chain of dominoes that does not fall all at once, but instead tips one piece at a time over days and weeks. This is not unprecedented. We have seen this kind of segmented stress migration before in other subduction systems. The 2004 Sumatra earthquake, magnitude 9.1, ruptured a massive segment of the Sunda Trench in the eastern Indian Ocean. 3 months later, a magnitude 8.6 struck the adjacent segment to the south. That was not coincidence. That was not bad luck. That was Coulomb stress transfer activating a neighbouring locked patch that had been brought closer to failure by the first event. The initial rupture changed the stress field. The adjacent segment, which might have held for years or decades more under the old stress conditions, was pushed past its threshold by the new ones, and it broke. The Kamchatka sequence in early 2025 showed similar cascade behaviour along a segmented subduction boundary. A large initial event followed by progressive activation of neighbouring fault segments in a directional pattern. The pattern is recognisable if you know what to look for, And the pattern the Kermadec Trench is showing right now fits squarely within that category. The system is not relaxing, it is reorganizing. And the direction of that reorganization points south, toward a subduction margin that sits directly beneath the seafloor off the east coast of New Zealand's North Island. But here is where this story becomes something larger than one migrating swarm in the southwest Pacific. Because at the exact same time that the Kermadec Trench was showing this directional stress migration, something else was happening 10,000 kilometres away, on the opposite side of the Pacific Ocean, along a fault that has not fully ruptured in 326 years. The Cascadia subduction zone just recorded 791 episodic tremor and slip events in a single day. Let that number register for a moment. 791. Not over a week, not over a month, in a single day. These are not ordinary earthquakes. They are not the kind of shaking you would feel at the surface. You would not wake up in the middle of the night. Your dog would not bark. Your phone would not light up with an emergency alert. These events occur at depths between roughly 25 and 45 kilometres, far below the locked portion of the megathrust fault, in a transition zone where rock behaviour shifts from brittle failure to slow ductile creep. This is where the fault does not snap. It slides, slowly, intermittently, in episodes that generate a specific type of low-frequency seismic signal that monitoring networks can detect but most people would never notice. If you were standing directly above one of these events, you would feel nothing. The ground beneath your feet would give no indication that the fault below was moving. And that is exactly what makes them so important. Because the things you cannot feel are sometimes the things that matter most. This is called episodic tremor and slip, or ETS, and it is one of the most important discoveries in subduction zone science in the last 25 years. It was first identified along Cascadia in the early 2000s, and it fundamentally changed how scientists understand the loading cycle of megathrust faults. Because what ETS represents is not the fault rupturing, it represents the fault preparing. The portion of the subduction interface that produces the tremor signal is not the locked zone that generates great earthquakes. It is the zone below the locked segment, where fluids trapped in subducted oceanic crust reduce friction enough to allow slow, episodic sliding. Think of it as a layer of lubrication at the base of the locked zone, a region where the fault can move without breaking, releasing small amounts of energy in controlled pulses rather than catastrophic snaps. And every time that zone slips, it does something mechanically critical. It transfers stress upward, into the locked zone, into the part of the fault that is accumulating centuries of elastic strain, into the segment that, when it finally does rupture, will generate one of the most powerful earthquakes and tsunamis the Pacific Northwest has ever experienced. The locked zone does not slip. It absorbs. It takes every increment of stress the ETS cycle delivers and adds it to the total already stored by 326 years of continuous plate convergence. And it holds. Because that is what locked zones do. They hold until they cannot hold anymore, and then they fail all at once. So now you have two signals happening simultaneously. The Kermadec system is showing lateral stress migration along a continuous subduction corridor. The Cascadia system is showing a spike in vertical stress loading from below. Two different mechanical regimes, two different directions of energy transfer. One is horizontal, stress sliding along a fault-like current through a wire. The other is vertical, stress pushing upward from a sliding zone into a locked one, both involving megathrust boundaries capable of producing magnitude 8 to magnitude 9 earthquakes, both active within the same narrow time window, both showing their respective fault systems in states of active internal reconfiguration. And that is the question that defines this entire story. What does it mean when two independent subduction systems, separated by 10,000 kilometers of open ocean, start showing internal deformation signals at the same time? The honest answer, the scientifically rigorous answer, is that we do not know with certainty whether it means anything at all. There is no established geophysical mechanism that directly couples the Kermadec Trench to the Cascadia subduction zone. They sit on different plate boundaries. They involve different tectonic configurations. They are driven by different plate motions, governed by different frictional regimes, and loaded by different convergence rates. The stresses in one system do not physically reach the other in any direct, measurable way. Earthquakes on opposite sides of the Pacific do not pull on each other like connected springs. There is no wire running between them, no shared loading mechanism, No tectonic link that would allow a rupture in Tonga to influence tremor behaviour in Oregon. And yet, the timing is hard to ignore, not because the timing proves anything, but because the Earth has a way of reminding us that our models are incomplete. Global seismicity does cluster. The Ring of Fire, that horseshoe-shaped belt of subduction zones, volcanic arcs, and transform faults encircling the Pacific Basin, has been unusually active in recent weeks. Multiple magnitude 6 and magnitude 7 events in diverse locations. Elevated volcanic unrest at several sites. The statistical reality is that tectonic activity is not evenly distributed in time. It comes in bursts and clusters, in periods of elevated output that are entirely consistent with random variation in a complex system. You can get streaks of activity without any underlying coordination, the same way you can flip a fair coin and get 7 heads in a row without the coin being rigged. The coin is not broken. The universe is not sending a message. Randomness just looks like a pattern sometimes, especially when you are the kind of species that evolved to find patterns in everything, because missing a real one could get you killed. But human perception does not process randomness well. When two dangerous systems show unusual behaviour at the same time, we instinctively search for a connection. We want the events to mean something together. We want a narrative that links them, because a connected threat feels more understandable than two independent threats that just happen to overlap in time. A single story with a single cause and a single trajectory is something the brain can grasp. Two unrelated stories that happen to coincide in a way that looks meaningful but may not be is harder to sit with. It feels incomplete. It feels like someone is withholding the explanation. The irony is that the disconnected version might actually be more unsettling, because it means the Earth's most dangerous fault systems do not need to be linked to be simultaneously dangerous. They can each, independently, be accumulating toward failure on their own timelines, and sometimes those timelines happen to produce visible signals at the same moment. Not because the universe is coordinating, but because there are so many active fault systems on this planet that the probability of two of them doing something interesting in the same week is not as low as you might think. It is just that most weeks, nobody is watching closely enough to notice. That is the uncomfortable coincidence problem at the centre of this story. Two megathrust systems, both showing internal stress signals, both capable of catastrophic rupture, both active right now, and no accepted physical mechanism connecting them. What we are left with is not a prediction, it is a perception problem. And the question is not whether these two systems are linked. The question is whether what each system is doing individually is enough to warrant the kind of attention that most people only give to earthquakes after the shaking has already started. Because here is what I can tell you with confidence. The Kermadec swarm is not behaving like a normal aftershock sequence. The directional migration, the linear stepping, the progressive southward movement along the trench axis, all of it points to a system that is redistributing stress rather than releasing it. And the Cascadia tremor spike, while it falls within the range of known ETS variability, is occurring during a period when that fault has been accumulating strain for over 3 centuries without relief. Neither of these observations constitutes evidence that a great earthquake is imminent, but both of them constitute evidence that these systems are active, that they are doing what subduction zones do between great earthquakes, and that the processes driving them toward eventual failure have not paused, have not slowed, and are producing signals that are measurable, real, and worthy of attention. If the rupture from Tonga did not release its energy locally, then where did it go? And if the answer is south, toward a subduction zone sitting off the coast of a country with 5 million people, then the next question is the one nobody wants to ask out loud. How far south can it reach? How many segments can this stress front activate? And what happens when a migrating stress pulse arrives at a fault boundary that is structurally complex, mechanically variable, and already storing its own accumulated strain from centuries of convergence? That is what we need to trace. And the Kermadec Trench is about to show us exactly how a subduction system behaves when stress starts moving through it like a slow motion chain reaction. Part 2. The thing you need to understand about the Tonga to Kermadec to Hikurangi fault corridor is that it is not 3 separate systems, it is one system with 3 names. We give different labels to different segments the way you might name different neighbourhoods in the same city. Useful for conversation, misleading for comprehension. Because what actually exists beneath the southwestern Pacific is a single, continuous subduction boundary stretching roughly 1,000 kilometres from the volcanic arc near Tonga in the north to the continental margin off New Zealand in the south. One plate, the Pacific, is diving beneath another, the Australian, along the entire length of this boundary, and the mechanical forces governing that collision do not stop and restart at the borders between our labels. Stress flows through this system the way current flows through a wire. It does not care what you call the segment it is passing through. It does not pause at the line where Tonga ends and Kermadec begins. It does not ask for permission to cross into Hikurangi territory. The rock is continuous, the interface is continuous, and the forces acting on that interface are continuous. The labels are ours. The physics belongs to the fault. This is the concept that turns the Tonga 7.5 from a regional event into something with systemic implications. If this were an isolated fault, a short disconnected segment with clear structural boundaries separating it from everything around it, then the earthquake on March 24th would be exactly what it first appeared to be. A major event followed by local aftershocks and gradual relaxation. End of story. The energy would stay local, the stress changes would dissipate within a relatively confined zone, and the surrounding segments would be mechanically unaffected. You could draw a circle around the rupture, study what happened inside that circle, and safely ignore everything outside it. That is how isolated faults work. They break, they calm down. The rest of the world does not notice. But the Tonga to Kermadec to Hikurangi system is not isolated. It is connected, continuously connected, along a subduction interface where the geometry, the convergence rate, and the frictional properties of the rock create conditions for stress to propagate laterally across enormous distances. And when a magnitude 7.5 ruptures one end of a connected system like this, the stress does not simply vanish at the edges of the rupture. It does not hit an invisible wall and stop. It loads onto the adjacent segments. It changes the Coulomb stress state on neighbouring fault patches. Some of those patches were already close to failure, sitting at 95 or 98% of their threshold, needing only a small nudge to tip them over. Some were far from it, stable and decades away from any concern. But the stress field has been rearranged, and the system has entered a new mechanical configuration that did not exist before March 24th. Every segment of this corridor is now operating under a different set of conditions than it was operating under 2.5 weeks ago, and the segments closest to the rupture are the ones that felt the change most acutely. That is what the monitoring data appears to be showing. The southward stepping pattern that emerged days after the initial Tonga rupture is not a random scatter of seismicity. It is an organised progression, multiple magnitude 5 and above events appearing at increasing distances from the original rupture, aligned along the trench axis, following the structural fabric of the subduction zone like water following a channel. Each event represents a local adjustment to the stress state imposed by the event before it. One segment shifts. That shift changes the stress on the next segment. That segment adjusts, and the adjustment changes the stress on the segment after that. The cumulative effect is a directional migration of activity that has a clear and measurable trajectory, not circular, not scattered, not radiating outward in all directions the way aftershocks do. Linear, progressive, one direction, south, toward New Zealand, toward the Hikurangi margin. Now, I want to be precise about what this does and does not tell us, because the difference matters enormously, and because this is exactly the kind of observation that gets distorted when it passes through the filter of social media and 24-hour news cycles. A migrating earthquake swarm is not a prediction. It is not a countdown. It does not mean that a larger earthquake is guaranteed at the end of the migration path, any more than a line of falling dominoes guarantees that the last domino will be bigger than the first. Migration tells you that stress is moving through the system. It tells you that segments are communicating. It tells you that the fault is not behaving as a collection of independent parts, but as a connected whole, in which changes at one point propagate to others. That is mechanically significant. That is worth monitoring. But it is not the same thing as a prediction, and anyone who tells you otherwise is selling something other than science. What it does tell us, and this is where the real significance lies, is something about the character of this fault system. Because the distinction between independent behaviour and connected behaviour is everything in subduction zone seismology. Independent fault segments fail on their own timelines, influenced primarily by local conditions. The stress on a given patch accumulates from local plate convergence, local frictional properties, local geometry. What happens on the segment next door is largely irrelevant. Each segment is its own story with its own timeline and its own probability of failure. Connected segments are a completely different animal. Connected segments fail in conversation with each other. The failure of one can accelerate, delay, or fundamentally alter the failure of the next. The stress field becomes a shared resource, a communal budget that gets redistributed every time one member of the system breaks. And in a connected system, you cannot evaluate the hazard of any single segment without considering what its neighbours are doing. The neighbourhood matters. The history of recent events on adjacent segments matters. The direction and magnitude of stress transfer matters. Everything becomes conditional on everything else. The Sumatra sequence in 2004 and 2005 was a connected failure. The initial 9.1 in December ruptured a massive segment of the Sunda Trench, one of the largest earthquakes ever recorded instrumentally. That rupture did not just release energy locally, it fundamentally rearranged the stress field along the entire surrounding plate boundary. And 3 months later, in March 2005, a magnitude 8.6 struck the adjacent segment to the south. That was not coincidence. That was not two unrelated events happening to occur in the same part of the world. That was Coulomb stress transfer activating a neighbouring locked patch that had been brought closer to failure by the first event. The initial rupture literally changed the conditions on the next segment, pushed it closer to its breaking point, and 3 months later, it broke. Not a prediction, not a certainty, but a mechanically coherent chain of causation that turned a single great earthquake into a multi-event rupture sequence spanning months and hundreds of kilometres of fault length. The Kermadec swarm is not yet in that category. Let me be clear about that. The magnitudes are smaller, the scale is different. We're not looking at a 9.1 followed by an 8.6. We are looking at a 7.5 followed by a southward migrating cluster of 5s and 6s. The energy levels are orders of magnitude lower. The implications are proportionally less dramatic. But the geometry of the migration is the same type. Directional, progressive, following the fault, not scattering randomly, not decaying in place, moving. And that pattern is what separates an aftershock sequence from a stress redistribution event. Aftershocks scatter, stress redistribution migrates. The Kermadec swarm is migrating. And once you recognise that distinction, the next question becomes unavoidable. So what sits at the receiving end of this migration? The Hikurangi subduction zone is where the Pacific Plate's journey beneath the Australian plate transitions from an oceanic trench environment to a continental margin. If you could drain the Pacific Ocean and stand on the seafloor east of New Zealand's North Island, you would see the trench shallowing, the geometry bending, the character of the subduction interface changing from a relatively simple oceanic collision to something far more structurally complex. Imagine walking along a flat, well-paved road and gradually stepping onto broken terrain. The interface that was relatively uniform along the Kermadec Trench becomes a patchwork. Thick wedges of sediment scraped off the descending plate pile up in what geologists call an accretionary prism, a chaotic jumble of deformed rock and ocean floor material that has been bulldozed off the Pacific Plate and plastered against the overriding plate over millions of years. The frictional properties along the interface become variable, changing over short distances from strongly locked to freely creeping. Zones of high coupling, where the plates are stuck together and accumulating strain, sit right next to zones of low coupling, where the plates slide past each other with relatively little resistance. The result is a patchwork of locked and creeping segments that makes the Hikurangi margin one of the most mechanically complicated subduction boundaries on the planet. This complexity matters because it determines how the margin responds to incoming stress. A simple, uniformly locked fault segment responds to increased stress in a relatively predictable way. It either holds or it does not. The analysis is straightforward. You calculate the stress change, compare it to the frictional strength of the locked interface, and estimate whether the fault is likely to hold or fail. But a complex margin with variable coupling, sediment subduction, and episodic slow-slip behaviour responds in ways that are far harder to forecast. Some of that incoming Coulomb stress from the Kermadec migration might be absorbed by slow slip on the weakly coupled portions of the interface bled off harmlessly in a seismic creep that nobody at the surface would ever notice. Some might be dissipated through microseismicity, tiny earthquakes too small to detect without sensitive instruments, scattered across the interface like static electricity discharging through 100 small sparks instead of one big bolt. And some might load onto strongly coupled patches that are already near their failure threshold, adding the final increment of stress to segments that were already holding on by a thin margin. The problem is that we do not know in advance which of these outcomes will dominate. We do not have sensors embedded in the fault interface. We cannot measure the frictional strength of locked patches in real time. We cannot determine from the surface whether a given portion of the Hikurangi margin is at 50% of its failure threshold or at 99%. The complexity that makes this margin scientifically fascinating is the same complexity that makes it hazardously unpredictable. What we do know is that the Hikurangi margin is capable of producing magnitude 8 to magnitude 9 earthquakes. That is not speculation. Geological evidence from uplifted marine terraces along the New Zealand coast, beaches and rocky platforms that sit meters above their expected elevation because the land was suddenly lifted by past megathrust ruptures, confirms that this subduction zone has generated catastrophic events in the geological record. Tsunami deposits, layers of ocean-transported sand found in coastal marshes and lagoons, far from the current shoreline, tell the same story from a different angle. The sea came inland, violently, repeatedly, over thousands of years. The exact recurrence intervals are debated, the segmentation patterns are uncertain, and the question of whether the entire margin can rupture in a single event or tends to fail in smaller segments remains one of the most actively researched problems in New Zealand seismology. But the capability is not in question. This is a megathrust. It has produced megathrust earthquakes before, and it will produce them again, and right now, a migrating stress front from the Tonga 7.5 appears to be propagating along the connected fault system in its direction. Every stepping event in the Kermadec swarm brings the activity closer to this transition zone, not as a guaranteed threat, not as a ticking clock, not as a prediction that New Zealand should brace for impact, but as a measurable change in the stress state of a system that was already storing strain from its own ongoing plate convergence. The Hikurangi margin did not need the Kermadec migration to be dangerous. It was already dangerous on its own terms. But the migration adds a variable. It introduces a perturbation to a system whose response to perturbation is difficult to predict. And in earthquake science, difficult to predict is not a phrase that inspires comfort. I want you to hold on to that framing, because it is going to matter in a few minutes when we talk about what is happening on the other side of the Pacific. The Kermadec migration is a lateral story. Stress moving horizontally along a connected boundary, propagating from one segment to the next in a chain of mechanical adjustments that stretches across hundreds of kilometers of ocean floor. But the Cascadia signal is a vertical story. Stress moving upward from below, pushed from a sliding zone into a locked zone, loading the fault not from the side but from underneath. Two different directions of the same fundamental process, the slow, relentless redistribution of mechanical energy through rock that can only absorb so much before something gives. But before we cross the Pacific, there is one more piece of the southwestern picture that deserves mention, and only mention, because it sits in the background of this story the way a loaded weapon sits on a mantelpiece in the first act of a play. You know it is there. You do not know when or whether it will go off, but you cannot pretend you did not see it. Running through the spine of New Zealand's South Island is the Alpine Fault, one of the most studied and most overdue strike-slip faults in the world. Its last major rupture occurred around 1717, roughly 309 years ago, and paleoseismic studies suggest it produces large earthquakes at intervals of roughly 200 to 300 years with remarkable regularity. It is, by many metrics, one of the most time-predictable faults on Earth in terms of recurrence, even though the exact date of its next rupture remains unknown. The Alpine Fault is not directly connected to the Hikurangi subduction zone. They are different types of faults, operating in different mechanical regimes, separated by a complex zone of deformation in the central part of New Zealand, where the tectonic style transitions from subduction to transform motion. But they exist in the same tectonic neighbourhood. They share the same general plate boundary, and some models suggest that significant stress changes on one could influence loading conditions on the other over long timescales. The question of whether offshore Kermadec stress migration could cascade through Hikurangi and eventually modulate conditions on the Alpine fault is the kind of multi-step, multi-system interaction that sits right at the edge of what current science can meaningfully evaluate. It is not a prediction, it is not even a strong hypothesis, but it is a reminder that fault systems do not exist in isolation, and the boundaries we draw between them on maps are often cleaner than the boundaries that exist in rock. The migrating swarm has a direction, that direction has a destination, and the destination is one of the most structurally complex and potentially dangerous subduction zones in the southern hemisphere, sitting in a tectonic neighbourhood that includes another major fault already, centuries past its average recurrence interval. That alone makes this sequence worth watching with more than casual interest. But what makes it worth examining in the kind of detail we are giving it today is the fact that this lateral migration is happening at the same time that a completely different megathrust system on the opposite side of the planet is showing its own distinct signal of internal stress redistribution. Not lateral this time, vertical, coming from below, loading a fault that last failed when the colonies that would become the United States were still governed by the British Crown. A fault beneath cities and towns where millions of people go about their daily lives with no awareness that the ground beneath them is quietly, incrementally, absorbing one more cycle of stress from a process they cannot see and cannot feel. 791 tremor events, one day, and a locked zone with 326 years of accumulated strain sitting directly above them, holding everything in place the way a dam holds back a reservoir. Solid, stable, reliable, right up until the moment it is not. Part 3. Somewhere between 25 and 45 kilometres beneath the Pacific Northwest, the Cascadia subduction zone is moving. Not the way most people imagine when they hear the word earthquake. There is no violent snap, no sudden displacement, no shockwave racing through the crust at kilometres per second. What is happening is slower, quieter, and in some ways more mechanically significant than any individual earthquake in the region. The interface between the descending Juan de Fuca plate and the overlying North American plate is slipping, incrementally, episodically, in bursts of low-frequency seismic tremor that last hours to weeks, release energy equivalent to moderate earthquakes and then stop, only to start again months later in a cycle that has been repeating with remarkable regularity for as long as modern instruments have been precise enough to detect it. This is episodic tremor and slip, ETS. And on the day that matters to this story, the Pacific Northwest Seismic Network recorded 791 of these tremor events in a single 24-hour period. To understand why that number is significant, you first need to understand what ETS is actually doing to the fault. The Cascadia megathrust, like all subduction megathrusts, is not a single uniform surface. It is a layered interface with different mechanical properties at different depths. Near the surface, and extending down to roughly 15 or 20 kilometres, the interface is locked. The two plates are stuck together, unable to slide past each other, accumulating elastic strain year after year as the Juan de Fuca plate continues its slow descent beneath North America. This is the seismogenic zone. This is the part of the fault that, when it eventually ruptures, will generate the catastrophic earthquake and tsunami that emergency planners in Oregon, Washington, and British Columbia have been preparing for. Below the locked zone, starting at roughly 25 kilometres and extending down to maybe 50, the character of the fault changes. The rock is hotter, the pressure is greater, fluids released from the subducting oceanic crust, water trapped in minerals that breaks free as temperature and pressure increase, permeate the interface and reduce friction. The fault in this zone does not lock the same way. It cannot store the same elastic strain. Instead, it slips. Periodically, episodically, in events that generate the tremor signal detected by surface seismometers. Understanding how seismologists actually detect these events requires stepping back from the geology and into the instrumentation. The tremor signal generated by ETS is different in character from the seismic signal of a regular earthquake. A typical earthquake, even a small one, produces a sharp, impulsive waveform, a clear P-wave arrival followed by a distinct S-wave, the kind of signal that stands out cleanly against background noise and allows precise location and magnitude determination. ETS tremor is nothing like this. It is emergent, broadband, low-frequency energy that waxes and wanes over periods of minutes to hours, It has been described as sounding like rushing water when converted to audio. It has no clean onset, no clean termination. Under the wrong conditions, it can be nearly indistinguishable from traffic noise, ocean microseisms, or industrial vibration picked up by shallow sensors. Detecting it reliably requires dense networks of seismometers and sophisticated signal processing algorithms. The Pacific Northwest Seismic Network, operated jointly by the University of Washington and the U.S. Geological Survey, maintains hundreds of such stations across Oregon, Washington, and southern British Columbia. Cross-correlating signals across multiple stations, filtering for the characteristic frequency bands of tremor, and applying template-matching algorithms against catalogued tremor signatures, the network can resolve individual tremor bursts lasting as little as a few minutes and locating them to within a few kilometers along the fault interface. It is the same basic principle as triangulation, applied with modern computational tools to signals that would have been invisible to seismologists even 30 years ago. ETS itself was only formally identified as a distinct phenomenon in the early 2000s. Herb Dragert and Gary Rogers at the Geological Survey of Canada, working with GPS data from the Western Canada Deformation Array, noticed something peculiar in the ground deformation records. At regular intervals, the surface of Vancouver Island was moving in the wrong direction. Instead of the slow, steady landward motion driven by plate convergence, the surface was periodically lurching seaward, as though something beneath it was momentarily releasing stored stress. The motion was small, millimeters to centimeters, and it lasted weeks before reversing. When they correlated this geodetic signal with seismic records, the tremor was there, coincident with every slip event, consistent in its frequency characteristics, systematic in its recurrence. They had found a new mode of fault behaviour, one that sat in the mechanical gap between stable creep and catastrophic rupture, and it had been operating beneath the most hazardous fault system in North America entirely undetected. The discovery fundamentally changed how seismologists thought about the megathrust cycle. Before ETS was recognised, the standard model of subduction zone behaviour was relatively straightforward. The locked zone accumulated strain. The transition zone crept steadily. The seismogenic zone eventually ruptured. The roles were fixed. The boundaries were clear. ETS complicated all of this, because it demonstrated that the transition zone was not simply creeping. It was engaging in a complex, quasi-periodic mechanical negotiation with the locked zone above, loading and unloading stress at regular intervals, communicating across depth in ways that the simplified model had not anticipated. And here is the mechanical reality that makes ETS so important. Every time the transition zone slips, it changes the stress state on the locked zone above. Think of it this way: the locked zone is being compressed from both sides. Below, the subducting plate drags against it. Above, the North American plate resists. The locked zone is caught in between, accumulating strain like a spring being wound tighter and tighter. Now, when the transition zone below slips episodically, it effectively applies a small additional load to the bottom edge of the locked zone. Not a dramatic load, not enough to trigger rupture on its own, but a measurable increment of stress transferred upward, cycle after cycle, year after year, adding to the strain already stored by 3 centuries of continuous plate convergence. The increments are small. Each individual ETS cycle transfers perhaps a few kilopascals of stress to the base of the locked zone. A trivial amount compared to the tens of megapascals believed to be stored there from centuries of plate convergence. But small increments, applied consistently over decades and centuries, are not trivial in their cumulative effect. Water torture is not painful because each drop hurts. It is painful because each drop adds to the last. The locked zone does not differentiate between the large sustained stress transferred from plate motion and the small pulsed stress transferred from below. It simply stores all of it, adds all of it, until the total exceeds what the interface can sustain. ETS is a loading mechanism, a hidden one, operating beneath the part of the fault that everyone worries about, feeding stress into the system from below while the plates above feed stress from the sides, and the locked zone absorbs it all, because that is what locked zones do. They absorb strain until they cannot absorb any more, and then they fail catastrophically in a matter of minutes. The 791 events in a single day represent unusually dense temporal clustering within this loading cycle. Northern Cascadia and Southern Cascadia segments both showed activity. this is not typical. The ETS cycle in northern Cascadia recurs at roughly 14-month intervals, and the clusters usually propagate from one end of a segment to the other over a period of weeks, the tremor migrating along strike at rates of kilometers per day in a pattern that suggests a fluid pressure front or a propagating slip pulse advancing through the transition zone. A single-day spike of this magnitude suggests a system-wide pulse of activity, not just one segment going through its normal cycle. Both ends of the system appear to be responding simultaneously, which implies either a shared triggering mechanism or a level of mechanical coupling between the northern and southern segments that the standard segmented model does not fully account for. The geometry of the Cascadia subduction zone does not make this simple. Unlike the relatively uniform Japan Trench, Cascadia is geometrically complicated. The subducting Juan de Fuca plate is not a single continuous slab. It is actually an assembly of smaller plate remnants, the Juan de Fuca proper, the Explorer plate to the north, the Gorda plate to the south, each with slightly different age, thermal structure, and angle of descent. The older and colder a subducting slab, the more negative buoyancy it has, the steeper it tends to subduct, and the deeper it tends to lock. The younger and warmer a slab, the more buoyant, the shallower the subduction angle, and the different the thermal structure of the interface. These variations in the subducting plate translate directly into variations in where the locked zone begins and ends, where the transition zone sits, and consequently where ETS occurs and how it behaves. The fact that both the northern and southern segments of this geometrically heterogeneous system showed elevated tremor activity on the same day is therefore not a trivially expected result. It requires either coincidence or communication. Now I need to be careful here, and I want you to be careful with me, because the space between what the data shows and what the data means is exactly where misunderstanding breeds. A 791 event day is unusual. It is a statistical outlier within the observed range of ETS behaviour, but ETS variability is high. The system does not produce identical cycles. Some are stronger, some weaker, some cluster more densely, some spread out. The duration of individual ETS episodes varies. The tremor rate within a given episode varies. The spatial extent varies. A single day of elevated tremor taken in isolation does not constitute evidence that the locked zone is about to fail. It is a data point, an interesting one, a noteworthy one, but a data point. What makes it more than a data point is context, and the context is 326 years. The last time the Cascadia megathrust ruptured was January 26, 1700. We know this with unusual precision for a prehistoric earthquake because of a convergence of evidence that reads like a detective story spanning centuries and oceans. Native oral histories along the Pacific Northwest coast describe a great shaking and flooding that wiped out coastal villages. The Huayat people of Vancouver Island, the Tillamook of the Oregon coast, the Quileute of Washington's Olympic Peninsula, each preserved in their oral traditions the memory of a catastrophe that came from the sea at night, without warning, after a great shaking of the earth. These are not vague references. They describe specific places, specific losses, specific observations of the way the coastline changed. They are consistent in their geography with what the geological record shows. That geological record is extensive. Layers of tsunami sand found in estuaries from Vancouver Island to Northern California indicate massive inundation, the kind that deposits identifiable marine sediment far above normal tide lines in a single abrupt event, separable in the stratigraphic column from the gradual sedimentation that occurs on either side. Ghost forests of drowned cedar trees killed by sudden coastal subsidence can be dated using dendrochronology, the outermost rings of the dead trees establishing the growing season in which they died, consistently pointing to the same narrow window in the late 17th century. The land along the coast dropped by as much as 2 meters in some locations in an instant, flooding lowland forests and preserving them as spectral stands of bleached snags, visible today in places like the Coppolis River estuary in Washington. And across the Pacific, Japanese historical records document an orphan tsunami, a tsunami with no local earthquake source that struck the coast of Honshu on January 27, 1700 Japanese time. Village records from coastal communities in the Sanriku region and elsewhere noted flooding without prior shaking, an anomaly that puzzled chroniclers at the time and that researchers centuries later recognized as the far-field signature of a distant great earthquake. Working backward from the travel time of the tsunami across the Pacific, From the known bathymetry of the ocean basins that would have shaped its propagation, scientists pinpointed the source to the Cascadia margin and the date to the evening of January 26th local time. The magnitude is estimated at approximately 9.0. The rupture likely extended along most or all of the roughly 1,000-kilometre-long subduction zone from Northern California to Vancouver Island. That was 326 years ago. The recurrence interval for full-margin Cascadia ruptures, estimated from turbidite deposits in deep ocean sediment cores, ranges from roughly 200 to 530 years. Turbidites are underwater landslides triggered by the shaking of a major earthquake, the sediment they deposit preserving a datable record of past ruptures that extends back thousands of years beyond any human memory or historical document. Different studies produce different ranges depending on methodology and which segments they examine, but the commonly cited average is somewhere around 200 to 300 years for some segments, with longer intervals for full-margin events that rupture the entire subduction zone simultaneously. The current elapsed time since 1700 places us within the expected window for some recurrence models and approaching it for others. This is not a prediction that the fault is about to rupture. I want to be explicit about that. Recurrence intervals are averages derived from a small number of past events. The turbidite record, while impressive in its depth, contains perhaps 40 recognisable events over 10,000 years. That is a sample size of 40 from which to infer statistical regularity for a system with known variability. They describe statistical tendency, not clockwork precision. The fault does not know what year it is. It does not have a timer. It responds to stress, and stress accumulates continuously without regard for human calendars. The 326-year figure tells us that the fault has had a long time to store strain. It does not tell us whether the current strain state is near the failure threshold or still far from it. We do not have strain gauges embedded in the locked zone. We cannot directly measure how close it is to rupture. What geodesy gives us is surface deformation, the slow bowing of the land surface above the locked zone as strain accumulates. GPS stations across the Pacific Northwest show the coast moving eastward, away from the trench, at rates of a few millimetres per year, consistent with elastic strain accumulation. The land surface is tilting. The coast is rising slightly relative to the interior. These signals are consistent with a fully or near fully locked megathrust, which tells us that strain is accumulating, but they cannot distinguish between a locked zone that has reached 90% of its failure stress and one that has reached 60%. The deformation field looks the same in either case. The sensitivity is not there. What we can measure is the process that feeds strain into the system, and right now, that process is showing an unusually active phase. There is a historical comparison that always surfaces in conversations about subduction zone tremor and subsequent great earthquakes, and it surfaces because it is genuinely relevant even though it is routinely overstated. In the months and years leading up to the 2011 Tohoku earthquake in Japan, a magnitude 9.0 that devastated the coast of northeast Honshu and triggered the Fukushima nuclear disaster, killing nearly 20,000 people and displacing hundreds of thousands more. Seismologists had observed changes in slow-slip behaviour along the Japan Trench, increased tremor activity, altered patterns of deep interface sliding, anomalous seismicity rates in the outer rise regions seaward of the trench. After the earthquake, some researchers looked back at these signals and argued that they represented precursory behaviour, early indicators of the stress state approaching criticality before the megathrust ruptured. The debate over whether those pre-Tohoku signals were genuine precursors or coincidental variations continues to this day. The honest assessment is that we do not yet have a reliable framework for distinguishing between tremor activity that precedes a great earthquake and tremor activity that precedes nothing at all. This is not a failure of seismology. It is a reflection of the fundamental difficulty of the problem. The physical processes that generate ETS operate continuously. The same type of signal occurs routinely without any subsequent megathrust rupture. It is part of the normal operating cycle of these faults. The challenge is that we do not know whether the amplitude, the spatial extent, or the temporal clustering of ETS can be used to forecast rupture likelihood with any operational precision. Some modelling studies suggest it can in theory, under specific assumptions about fault rheology and stress state. No observational study has demonstrated it reliably, in practice, across multiple fault systems and multiple rupture cycles. The seismological community is not comfortable with this gap, but it is honest about it. The field of earthquake forecasting has a troubled history, marked by premature claims and public misinterpretations that have periodically damaged the relationship between scientists and the populations they are trying to protect. The L'Aquila case in Italy, where scientists were initially convicted of manslaughter for allegedly failing to warn of a destructive earthquake, and then acquitted on appeal, illustrated with painful clarity how dangerous the interface between probabilistic scientific communication and public expectation can become. The community has responded by becoming more cautious, more explicit about uncertainty, more reluctant to translate observed anomalies into public warnings without a robust framework of evidence behind them. This caution is appropriate. It is also sometimes its own kind of communication failure. When a scientist says that an elevated tremor rate does not constitute evidence of imminent rupture, they are being accurate, but they are also not saying that it is meaningless. The space between those two positions is where the public most needs guidance, and it is precisely where scientific institutions are most hesitant to venture. So the Tohoku comparison is fair as a structural analogy. Both Cascadia and the Japan Trench are subduction megathrusts. Both exhibit deep tremor behavior. Both are capable of magnitude 9 events with associated tsunamis that would threaten coastal populations with little warning time. The Pacific Northwest has roughly 15 to 20 minutes of warning between the moment a full margin Cascadia rupture begins and the moment the first tsunami waves reach the coast. 15 to 20 minutes to move from wherever you're standing to whatever high ground exists within reach. For the low-lying coastal communities of Oregon and Washington, that interval is brutally short. For some areas, it may not be enough regardless of what anyone does. But the comparison is not a prediction. It is a reminder that the signals we are seeing along Cascadia have occurred in other systems that eventually ruptured catastrophically, without telling us whether Cascadia's current signals fall into the same category, or into the much larger category of normal cyclical behaviour that continues indefinitely without escalating to great rupture. What it does tell us is that the system is active. The loading mechanism is operating. Stress is being transferred upward into a locked zone that has been accumulating strain for over 3 centuries. And the ETS spike, the 791 event, is the latest pulse in a process that has been repeating for decades, but is now occurring during a period when the Ring of Fire as a whole is showing elevated seismic output. The Kermadec system in the southwest Pacific has been producing a migrating swarm of large earthquakes, the events propagating laterally along the arc in a pattern consistent with stress transfer along a connected fault system. The Aleutian chain has been restless. Tonga has been active. The Western Pacific subduction systems from the Philippines Trench to the Mariana Arc have collectively produced more large earthquakes in the preceding months than the same interval in an average year. And this is where the story returns to the central question. The Kermadec system is migrating laterally. The Cascadia system is loading vertically. Both are megathrust subduction zones. Both are showing signals of internal stress redistribution. Both are active right now. The Kermadec system shows a fault communicating along its length, stress transferred horizontally from one segment to the next in a kinematic cascade. The Cascadia system shows a fault communicating across its depth, stress transferred vertically from the transition zone to the locked zone in a mechanical loading cycle. 2 axes of the same fundamental process, occurring simultaneously on opposite sides of the largest ocean on Earth. The timing of the Cascadia ETS spike does not, by itself, suggest that the megathrust is approaching failure. The Ring of Fire is always doing something somewhere, and temporal clustering of seismic activity across different plate boundaries is a statistical reality that does not require a shared cause. Earthquakes are not evenly distributed in time. They cluster, they bunch. They produce periods that look anomalously active simply because random processes generate apparent patterns that our brains are exquisitely wired to detect and interpret as meaningful. This is not a weakness of human cognition in some abstract sense. It is the specific cognitive architecture that allowed our ancestors to identify the tiger in the tall grass before they had consciously registered the sound that triggered the alertness. Pattern recognition is survival. But it is also, when applied to complex stochastic systems, a reliable generator of false positives. But there is a difference between dismissing a pattern and understanding it. The pattern here is real. The Kermadec swarm is really migrating. The Cascadia tremor spike is really elevated, the Ring of Fire is really showing a period of elevated collective activity. And the question of whether these signals are coincidental or correlated, whether they reflect independent processes that happen to cluster in time, or whether they represent a shared response to some common perturbation of the stress field, is a question that leads us away from the solid ground of established seismology and into territory that most geophysicists would rather avoid discussing in formal publication, even if they discuss it in the hallways after the session ends. Because while two fault systems on opposite sides of the Pacific were showing these internal stress signals, something was arriving from 93 million miles away. Something with enough energy to compress the magnetosphere, to drive currents through the ionosphere, to induce voltages in long conductors at the surface of the Earth. Something that interacts with the planet not just atmospherically but electromagnetically, reaching down through the crust in ways that are still incompletely characterized, still debated, still the subject of research that sits in the uncomfortable zone between mainstream geophysics and the fringes where extraordinary claims require extraordinary evidence that has not yet arrived. A geomagnetic storm just hit Earth, and the timing, for better or worse, is impossible to ignore. The storm was not unexpected. Solar activity had been elevated for weeks, a consequence of the Sun approaching the peak of its 11-year activity cycle, a period during which sunspot numbers are high, coronal mass ejections are more frequent, and the probability of significant geomagnetic disturbance at Earth increases substantially. The specific event was a coronal mass ejection that left the solar surface 3 days earlier and travelled at roughly 800 kilometers per second through the interplanetary medium, its arrival tracked by monitoring satellites positioned at the L1 Lagrange point between the Sun and Earth, one of the few positions in space that gives humanity a direct look at what the solar wind is delivering before it arrives. The KP index, the planetary geomagnetic activity index that runs from 0 to 9, reached 7. Not the most powerful storm in the observational record, not a Carrington-level event, but significant enough to produce visible auroras at latitudes as low as 30 degrees, significant enough to produce measurable ground-induced currents in the Earth's crust, and significant enough to reignite a decades-old debate about whether solar electromagnetic forcing plays any role in modulating seismic activity. The debate is older than most people realise, and more scientifically serious than its popular reputation suggests. It has been advanced and retracted, and advanced again as data quality improved and analytical methods became more sophisticated. What it has not been, despite considerable effort on both sides, is resolved. And that unresolved status means that when a geomagnetic storm of KP7 arrives on the same day that the Cascadia system produces its most elevated single-day tremor count in years, the question is not whether there could be a connection. The question is whether we have the tools to know, and the honest answer, which is the only kind worth giving, is that we do not. Not yet. Not with confidence. What we have instead is a fault system that is loaded, a loading mechanism that is active, a regional context that is elevated, and an external forcing event that arrived at a moment when all of that was already in motion. Whether the storm is signal or noise in this story is a question the Earth will eventually answer. It answers all questions eventually. The only variable is whether anyone is watching carefully enough to understand what it says when it does. Part 4. The Sun did something unremarkable this week, and the consequences might be more interesting than anyone expected. A coronal hole, which is a region in the Sun's upper atmosphere where the magnetic field opens outward into space instead of looping back to the surface, released a high-speed stream of solar wind that has been washing over Earth's magnetosphere for the past several days. This is classified as a G1 geomagnetic storm, which is the lowest category on the National Oceanic and Atmospheric Administration's 5-level scale. G1 storms are common. They happen multiple times per month during active phases of the solar cycle, and the Sun is currently near the peak of solar cycle 25, so elevated solar wind conditions and minor geomagnetic disturbances are essentially the background noise of the current space weather environment. To understand what a coronal hole actually is requires a brief detour into solar physics that is worth taking, because the mechanism matters to what comes later. The Sun's magnetic field is generated by convective motion in its outer layers, plasma rising and falling and twisting in patterns driven by differential rotation, the equator spinning faster than the poles, the whole system producing a dynamic, constantly reconfiguring magnetic structure that never quite settles into a stable geometry. Most of the time, the field lines that emerge from the solar surface arc back to the surface in closed loops, confining the hot plasma of the corona in those loops and preventing it from escaping into space. But in some regions, the field lines do not close. They extend outward, past the point where the solar wind can sweep them back, and through these open field regions the corona drains freely into interplanetary space at speeds that can reach several hundred kilometers per second, substantially faster than the average solar wind velocity that permeates the inner solar system even during quiet periods. This outflow is the high-speed stream. It is not an explosion or an ejection. It is more like a sustained exhalation, a region of the sun breathing out continuously as long as the coronal hole persists. Coronal holes can last for weeks to months. As the sun rotates on its roughly 27-day period, a persistent coronal hole sweeps past Earth's position in its orbit repeatedly, each passage delivering another high-speed stream, another interval of elevated solar wind conditions, another minor perturbation to the magnetosphere. The current hole has been active for several rotations, which means the current G1 storm is not an isolated event, but the latest in a series of similar disturbances, a periodically repeating influence on the near-Earth space environment that has been operating as a background condition, while the seismic signals we have been tracking developed and evolved. Under normal circumstances, a G1 storm barely warrants a headline. It can produce minor fluctuations in power grid systems at high latitudes, where ground-induced currents flowing through transmission infrastructure can create voltage irregularities that operators monitor but rarely need to act on. It might push the aurora a few degrees closer to the equator than usual, briefly making the northern lights visible to populations that normally see them only during stronger events. Satellite operators note the elevated electron flux and make minor adjustments to orbital maintenance schedules, since elevated particle bombardment increases drag on low Earth orbit spacecraft and accelerates the degradation of solar panels. Radio operators at high frequencies note increased ionospheric absorption that can disrupt some communication bands. And within a day or two, conditions return to baseline. The magnetosphere recovers, the auroral oval retreats poleward, the satellite operators stop logging elevated flux, and the space weather forecast shifts back to green across all indices. This is routine. This is Tuesday. During solar maximum, G1 conditions occur so frequently that the space weather community essentially treats them as the default state rather than as discrete events. The forecasting centres at NOAA's Space Weather Prediction Centre in Boulder and at the European Space Agency's Space Weather Service Network issue their advisories, the power companies and satellite operators read them, appropriate adjustments are made, and life continues without interruption for the overwhelming majority of humanity that is either unaware these storms are happening or aware and correctly unconcerned. But the timing of this particular storm coincides with the seismic signals we have been tracking across two hemispheres, and that coincidence raises a question that the geophysics community has been debating, quietly and with considerable discomfort, for decades. Can space weather influence earthquake timing? Let me be clear about where this sits on the scientific credibility spectrum before we go any further, because this is exactly the kind of topic where precision matters, and where the gap between legitimate research and wild speculation is narrower than most people realise and easier to cross than it should be. There is no established, consensus-supported mechanism by which geomagnetic storms trigger earthquakes. The energy budget does not work. A G1 geomagnetic storm deposits energy into the magnetosphere that is many orders of magnitude smaller than the energy stored in a tectonically loaded fault. The total energy input from a G1 event to the coupled magnetosphere-ionosphere system is on the order of 10 to the 15 joules. The energy released by a magnitude 8 earthquake is on the order of 10 to the 17 joules. The energy stored in the locked zone of the Cascadia megathrust over 3 centuries of plate convergence is orders of magnitude larger still. The idea that a solar wind gust could cause a magnitude 7 earthquake makes about as much physical sense as suggesting that breathing on a dam could cause it to burst. The dam fails because of the millions of tons of water behind it, not because of the air pressure from someone standing in front of it. The proportions are not even close, and yet. There is a body of peer-reviewed research, small but not negligible, that explores a more nuanced version of this hypothesis. Not solar triggering of earthquakes, solar modulation of earthquake timing. The distinction is critical, and it is the distinction that gets lost almost immediately whenever this topic escapes the confines of academic discussion and enters the broader information environment. Nobody serious is arguing that the sun causes earthquakes, tectonic forces cause earthquakes, plate convergence causes earthquakes, centuries of accumulated elastic strain cause earthquakes. The sun has nothing to do with why the Cascadia megathrust is loaded to the level it is loaded to today. 326 years of plate convergence caused that. But the question of whether external perturbations, however small, can influence the precise timing at which an already critical fault system finally ruptures is a different question entirely. And it is a much harder one to dismiss categorically, because it is asking something fundamentally different about the nature of failure in complex mechanical systems. The proposed mechanism works like this. Geomagnetic disturbances induce variations in Earth's external magnetic field. The magnetosphere compresses on the day side and extends on the night side as the enhanced solar wind pressure reshapes it, and these geometric changes propagate downward in the form of variations in the surface magnetic field that are detectable with standard magnetometers. These variations, through electromagnetic induction, the same basic physics as a transformer or a generator coil, generate telluric currents in the crust. Telluric currents are real, measurable, well-documented phenomena. They have been studied since the 19th century, initially because they interfere with telegraph and later telephone systems, and more recently because they represent both a hazard to power infrastructure and a potential tool for probing the electrical conductivity structure of the crust. They flow through conductive pathways in the upper lithosphere, following zones of elevated conductivity like fluid-saturated fault zones, sedimentary basins, and regions of partial melt. Their intensity increases during geomagnetic storms. This is not a fringe claim. It is textbook electromagnetic geophysics. Some researchers have hypothesized that these induced currents could modulate pore fluid pressure in fault zones, alter the electrical properties of mineral interfaces in ways that change frictional behavior, or produce very small piezoelectric stresses in quartz-bearing crystalline rock through the interaction between the electrical field and the crystal lattice. Each of these effects, if real, would be tiny, negligible compared to tectonic forces. But the hypothesis is not that they push the fault to failure from a stable state, as if the sun were the proximate cause of rupture. The hypothesis is more targeted and more defensible than that. It is that these effects could nudge a fault that is already at the very edge of failure, one that would rupture within days or weeks regardless, into rupturing slightly sooner rather than slightly later, changing the when, not the whether, shifting the distribution of rupture timing within a window that tectonic loading has already determined. This is the concept of marginal triggering, the idea that for a fault system already at 99.9% of its failure threshold, already at the knife edge between locked and catastrophically sliding, even an infinitesimally small additional stress perturbation could serve as the final increment that tips the system from one state to the other. The analogy that physicists sometimes use is the critical point in a phase transition. At exactly the temperature and pressure where water converts to steam, the system is exquisitely sensitive to tiny perturbations. A single photon of the right energy can nucleate the transition. The photon is not causing the phase change in any thermodynamic sense. The enthalpy difference between the phases is doing that, but the photon can determine exactly when and where the transition begins. Whether this analogy applies to fault rupture nucleation is debated. Whether fault systems actually reach a state of true criticality before rupture, or whether rupture nucleation involves more complex dynamics that make the critical point analogy misleading, is an open question in earthquake physics. Tidal forces, which are vastly larger than any solar-induced electromagnetic stress, and which operate through a clear, well-understood gravitational mechanism, have been shown to have a weak but statistically detectable correlation with some types of seismicity. The signal is clearest for shallow extensional earthquakes and for certain classes of volcanic seismicity. It is present but less pronounced for thrust earthquakes and subduction zone events. It is essentially undetectable for deep earthquakes. The tidal stress variations that produce these correlations are on the order of a few kilopascals, a few thousandths of 1% of the stress drop in a typical moderate earthquake, and yet over large catalogues and many earthquake cycles they leave a measurable imprint on the timing distribution of events. If stresses this small can modulate earthquake timing at the margin, the argument goes, then it is at least conceivable that other small periodic stresses could as well. The electromagnetic stresses from telluric currents are smaller than tidal stresses. Probably. The estimates vary because the relevant parameters, pore fluid conductivity, fault zone electrical structure, the coupling between electrical and mechanical stress, are poorly constrained at the depths and pressures that matter. The research on solar seismic correlations is inconclusive, and inconclusive is a word that requires some unpacking, because it is doing a lot of work in that sentence. In science, inconclusive can mean many things. It can mean the data are too noisy to see any signal that might be there. It can mean that studies have found positive and negative results in roughly equal measure, suggesting the truth might be near zero. It can mean that methodological variability between studies makes their results impossible to compare. In the case of solar seismic correlations, it means something close to all three simultaneously. Some studies find statistically significant correlations between geomagnetic indices and earthquake occurrence rates. A 2020 analysis of global earthquake catalogues found that the rate of magnitude 5.5 and larger earthquakes showed a weak but statistically significant elevation in the days following geomagnetic storms, with the signal concentrated in regions of high crustal conductivity. A separate analysis of intermediate depth seismicity in subduction zones found a similar pattern. Others find no correlation at all, or find that apparent correlations disappear when the statistical analysis is corrected for the temporal clustering of earthquakes themselves, which means that a period of elevated seismicity following a geomagnetic storm might simply reflect the aftershock productivity of earthquakes that occurred independently of the storm. The results depend heavily on the time window examined, the earthquake catalogue used, the statistical methodology applied, the magnitude threshold employed, and the definition of what constitutes a geomagnetically active period. No study has demonstrated a reliable predictive relationship. No study has established a clear physical mechanism that operates at the right scale, in the right direction, with the right timing to account for the correlations that have been reported. And no mainstream seismological organisation incorporates solar activity into hazard assessments, because doing so without a robust mechanistic foundation would introduce noise into decision systems that require clarity. But the research continues because the question is genuinely interesting and genuinely unresolved. It continues because the researchers working on it are not fringe figures. Several of the papers in this literature come out of respected institutions, have passed peer review at journals with rigorous standards, and have been cited by other researchers without the kind of dismissive academic framing that typically accompanies work considered beyond the pale. And it continues because the timing correlations, while statistically weak and inconsistent across studies, keep appearing in different datasets examined by different groups using different methods. They are not strong enough to build a forecasting system on. They are not consistent enough to constitute proof of a causal mechanism. They do not survive every methodological test applied to them. But they are persistent enough that simply declaring the hypothesis dead requires a more thorough and systematic demolition than the field has yet undertaken, and that demolition has not been undertaken perhaps because the hypothesis is not taken seriously enough to be worth the effort, or perhaps because the people who have looked most carefully at the data are not entirely comfortable declaring it dead. The sociology of science matters here. Research programs survive or die not only on the strength of their evidence, but on the professional environments in which their practitioners work, the funding structures that support or discourage certain questions, and the reputational risks that attach to association with particular topics. Solar seismic coupling sits in an uncomfortable neighbourhood. On one side are geophysicists doing rigorous quantitative work on a hypothesis that mainstream opinion considers unlikely. On the other side are astrologers, earthquake predictors with zero track records, and YouTube channels that confidently announce imminent catastrophes based on sunspot counts. The proximity of the legitimate research to the illegitimate noise creates a social incentive for serious scientists to distance themselves from the topic, even when their data might point towards something worth examining more carefully. This is not a conspiracy. It is just how scientific communities manage their reputational economies, and it is worth naming because it means that the absence of mainstream consensus on this topic is not the same as the absence of evidence worth taking seriously. Now, how does this apply to what we're seeing right now? The Cascadia ETS zone exists at a depth and in a mechanical regime where small stress perturbations have the greatest theoretical potential to matter. The transition zone between locked and creeping behaviour on a subduction interface is, by definition, a region of marginal mechanical stability. The frictional properties of the interface in this zone are balanced on a knife edge between velocity-strengthening behaviour, which promotes stable seismic sliding, and velocity-weakening behaviour, which promotes unstable seismic slip. This balance is maintained by the particular combination of temperature, pressure, mineralogy, and fluid content that characterises the fault interface at these depths. The presence of fluids is especially significant. High pore fluid pressure reduces the effective normal stress on the fault interface, which reduces friction, which lowers the threshold for sliding. Small changes in pore pressure, whether from tidal loading from episodic fluid release from the subducting slab, or hypothetically from electrically induced changes in fluid flow pathways, would have a proportionally larger effect on a high pore pressure interface than on a dry, high normal stress fault segment closer to the surface. If there is any environment on Earth where a tiny external modulation could theoretically influence the timing of slow slip events, the ETS zone of a subduction megathrust is among the most physically plausible candidates, not because the energy balance works in any direct sense, it still does not. The tectonic forces remain overwhelmingly dominant, but because the system is operating near a mechanical threshold, is sensitive to small perturbations by definition, and contains high-pressure fluids that could in principle respond to electromagnetic-induced stress changes in ways that slightly alter the timing of slip initiation. The question of whether this sensitivity extends to megathrust rupture itself, or whether it is confined to the slow slip regime, is a separate and much harder question that requires understanding how ETS and locked zone failure are coupled, which is itself incompletely understood. Does that mean the geomagnetic storm caused the 791 event day? No, almost certainly not. The reasoning is straightforward even if the science is complicated. The ETS system has produced large event days before, during geomagnetically quiet periods, during solar minimum, during intervals with no significant space weather activity at all. The correlation, if it exists, would be subtle, statistical, detectable only over large datasets spanning many ETS cycles and many geomagnetic storm events, requiring careful controlling for the natural variability of the ETS system itself before any external signal could be isolated. It would not be visible in a single day's data from a single storm and a single elevated tremor count. The confounding factors are too numerous. The natural variability of the system is too large. And the tectonic forces driving Cascadia's ETS cycle are so overwhelmingly dominant that any solar contribution would be like adding a teaspoon of water to a swimming pool. Real in principle, unmeasurable in practice on any given day against any given backdrop of tectonic noise. But the timing creates a narrative, and narratives have consequences that extend beyond the people who are paying careful attention. When seismic activity is elevated and a geomagnetic storm arrives, and social media algorithms detect rising engagement on earthquake-related content, the combination produces something that the scientific community dreads but has never fully figured out how to prevent: a perfect environment for the rapid amplification of misinformation. The dynamics are well understood even if they remain difficult to counter. A real event, in this case an elevated ETS count that is genuinely scientifically interesting, provides the seed of legitimate concern. A coincident phenomenon, in this case the geomagnetic storm, provides an apparently explanatory connection. The explanation, while speculative, has just enough surface plausibility to be shareable. Sharing generates engagement. Engagement signals the algorithm. The algorithm amplifies to wider audiences. Wider audiences include people with larger followings who have built those followings by offering confident explanations of scary things, and those people do not require scientific rigour before broadcasting. Within hours, what began as a data point in a seismic monitoring bulletin has become evidence of an imminent catastrophe that the government is hiding. This is worth addressing directly, not because conspiracy theories deserve equal airtime with physics, but because the fear and confusion they generate are real even when the theories are not. People make decisions based on fear. They call family members in coastal areas and tell them to evacuate. They flood emergency management hotlines with inquiries that draw resources away from actual preparedness activities. They lose trust in scientific institutions not because those institutions failed them, but because the information environment surrounding those institutions has become so polluted with confident false claims that distinguishing between them and cautious accurate ones requires more epistemological effort than most people have been trained to invest. Every time there is a visible cluster of earthquake activity anywhere on the Ring of Fire, social media fills with several predictable categories of claims: that the earthquakes were engineered through directed energy weapons, a claim that requires ignoring both the physics of energy coupling into the Earth's interior and the complete absence of any evidence of such technology existing; that governments are suppressing seismic data to prevent panic, a claim that requires believing that every national seismological network, university seismology department, and independent monitoring organisation across dozens of countries is coordinating a cover-up in real time; that patterns in seismic data, usually presented as maps with lines drawn between earthquake epicenters, prove coordinated manipulation, a claim that requires believing that whoever is engineering the earthquakes is doing so in a way that creates visible geometric patterns, visible to amateur observers on social media, but somehow missed by professional seismologists. These claims have no scientific basis, none. Earthquake prediction is not currently possible with any method that has demonstrated operational reliability. No technology exists to trigger tectonic earthquakes at the scales we are discussing. The energy required to nucleate rupture on the Cascadia megathrust would exceed the annual energy output of human civilization by multiple orders of magnitude. The physics is not ambiguous on this point. What is ambiguous, and what inadvertently feeds the conspiracy ecosystem, is the legitimate scientific uncertainty that surrounds earthquake science. When seismologists say they cannot predict earthquakes, when they describe recurrence intervals as wide ranges rather than specific dates, when they acknowledge that simultaneous activity on distant faults might be coincidence or might reflect poorly understood processes, when they say honestly that the relationship between ETS and megathrust rupture is incompletely characterized, the uncertainty itself becomes fuel for alternative explanations. For people who have learned, sometimes for good historical reasons, to distrust institutions, scientific uncertainty sounds like evasion. The honest answer, which is that we do not fully understand these systems and are working toward better understanding with incomplete tools and imperfect data, gets reinterpreted through the lens of institutional distrust as the suspicious answer: they know more than they are telling you. This interpretive inversion, where honesty about uncertainty is read as evidence of concealment, is one of the most corrosive dynamics in contemporary science communication, and it has no easy solution. Becoming more confident and less hedged does not work, because it replaces honest uncertainty with dishonest certainty, and when the confident prediction fails to materialize, trust erodes further. Becoming more detailed and more technical does not work because it increases the distance between scientists and the publics they are trying to reach. Ignoring the misinformation ecosystem does not work because information vacuums fill. The challenge of communicating what earthquake science actually knows, what it honestly does not know, and why the gap between those two categories is not a conspiracy, but a reflection of how genuinely hard the underlying science is, represents one of the more important unsolved problems in science communication, operating at a moment when the stakes of getting it wrong are unusually high. The truth is simpler and more frustrating than either the conspiracy narrative or the dismissive institutional response. We understand the physics of earthquakes quite well at the level of fundamental mechanics. We understand the principles of elastic rebound theory, the mechanics of fault friction, the thermodynamics of the brittle ductile transition, the stress transfer dynamics of earthquake sequences. We understand the mechanics of subduction zones at a level of detail that would have seemed extraordinary to the geologists of 50 years ago, before plate tectonics was even fully accepted. What we cannot do is translate that mechanistic understanding into reliable prediction, because the systems are chaotic, because the initial conditions are unknown and unknowable with existing technology, because the variables that determine whether a fault ruptures today or in 50 years are buried tens of kilometers beneath the surface, where no instrument can directly sample them. The gap between understanding the physics and being able to predict the outcome is not a gap that better intentions or more funding will quickly close. It is a fundamental feature of the problem. So the geomagnetic storm is real. The hypothesis of solar seismic coupling is real, though unproven and contested and sitting in an uncomfortable position in the scientific literature. The Cascadia ETS spike is real. The Kermadec migration is real. The Ring of Fire is showing a period of elevated collective activity that is statistically notable, even accounting for the clustering tendencies of seismic systems. The temptation to draw a single connecting line through all of these phenomena is understandable, because the human brain is extraordinarily good at finding patterns and extraordinarily poor at evaluating whether the patterns it finds are causal or coincidental, and the responsibility to resist that temptation without sufficient evidence is not a counsel of passivity or institutional defensiveness. It is a prerequisite for thinking clearly about hazard. Premature connections crowd out the actual science, generate unfounded fear, and make it harder to communicate genuine risk when the genuine risk is elevated in ways that evidence actually supports. What we should be focused on, and what the next part of this story will attempt to clarify, is what these signals actually tell us about the individual behaviour of two fault systems that are each, on their own terms, worth watching very carefully right now. Not because of what a geomagnetic storm may or may not do to their stress states, not because of the narrative convenience of their simultaneous activity, but because the long-term tectonic loading of these systems, considered independently and rigorously, is itself sufficient reason for careful attention without any additional embellishment from space weather or pattern-seeking cognition. The Cascadia megathrust does not need a geomagnetic storm to be dangerous. It is the most dangerous seismic structure in North America on its own terms, driven by its own physics, loaded by its own tectonic history. The Kermadec system does not need a solar connection to justify monitoring. It is a highly active subduction zone, capable of great earthquakes that would threaten island communities across the Southwest Pacific, because the answer to the question of what these two systems are doing simultaneously is scientifically interesting and possibly significant, and worth continued careful observation. But the answer to the question of what each system is doing individually is the thing that actually matters to the people who live within reach of what either system can do when it stops loading and starts moving all at once. Part 5. Here is what we know, stripped down to the mechanics, with the speculation set aside and the physics left standing on its own. The Kermadec Trench is showing lateral stress migration. The Cascadia subduction zone is showing elevated vertical loading. These are two different fault systems operating in two different mechanical regimes on opposite sides of the Pacific Ocean, and the simultaneity of their current signals creates a perception of coordination that the available evidence does not support. But perception, in this case, is not the problem. The problem is that each of these signals, evaluated independently, tells a story about a fault system in a state of active stress redistribution. And active stress redistribution on a megathrust subduction zone is the kind of process that warrants attention, regardless of what any other fault on the planet is doing at the same time. Let me separate them. The Kermadec system is showing a pattern of seismicity that is inconsistent with simple aftershock decay and consistent with Coulomb stress transfer along a continuous subduction boundary. To understand why this distinction matters, it helps to understand what normal aftershock sequences look like and why this one does not fit that description. After any significant earthquake, the surrounding crust adjusts to the sudden redistribution of stress through a series of smaller earthquakes. These aftershocks follow a remarkably consistent statistical pattern described by the Omori-Utsu law, in which the rate of aftershocks decays approximately as the inverse of time since the main shock. They cluster tightly in space around the main shock rupture zone, filling in the areas immediately adjacent to the rupture where stress was concentrated by the main shock slip. They decrease in magnitude as the sequence progresses, with occasional larger events that reset the decay clock locally, but do not reverse the overall trend toward quiescence. And critically, they do not migrate. The spatial centroid of an aftershock sequence may shift slightly as the sequence fills in the available stress concentration, but the systematic directional migration of significant events over days to weeks, moving away from the main shock in a coherent direction, is not a feature of ordinary aftershock sequences. It is a feature of stress transfer. The southward stepping pattern of magnitude 5 plus events following the March 24th Tonga 7.5 suggests that segments of the fault south of the initial rupture are adjusting to a new stress field imposed on them by the main shock. Coulomb stress transfer is the mechanism. When a fault segment ruptures, the static stress field around the rupture changes permanently. Regions that were clamped by the pre-rupture stress field may be unclamped. Regions that were in the stress shadow of adjacent locked patches may receive additional load. The Coulomb stress change on any given receiver fault depends on the geometry of both the source rupture and the receiver fault, the orientation and rake of the receiver relative to the regional stress field, and the frictional properties of the receiver interface. For receiver faults that are optimally oriented relative to the stress change, even small Coulomb increments of a tenth to a few tenths of a bar can be sufficient to advance the seismic cycle by years to decades, effectively moving those segments closer to their failure threshold. For receiver faults that are suboptimally oriented, the transferred stress may actually inhibit rather than promote failure. The migration we are observing suggests that the receiver faults south of the Tonga rupture are favourably oriented to receive stress from the main shock, and that the transferred stress is sufficient to drive seismicity along a connected corridor. This does not mean a larger earthquake is coming. It does not mean the Hikurangi margin at the southern end of this system is about to rupture. Stress transfer is a necessary but not sufficient condition for triggered seismicity on adjacent segments. Many stress transfer events load neighbouring faults without producing further significant earthquakes, because those faults, while receiving additional stress, are not yet near enough to their own failure thresholds for the increment to matter in any practical sense. The receiving segment must already be near its failure threshold for the transferred stress to tip it over the edge. If it is not, the additional load simply becomes part of the background strain accumulation, adding a small increment to a total that might not reach critical levels for decades or centuries. The honest scientific assessment of where the Hikurangi margin currently sits relative to its failure threshold is, we do not know with any precision. The Hikurangi subduction zone, which runs along the east coast of New Zealand's North Island and accommodates the convergence of the Pacific and Australian plates at this latitude, has its own complex history of great earthquakes, slow slip events, and ETS-like behaviour. The offshore portion of the Hikurangi margin in the northern North Island is particularly interesting to researchers because it exhibits shallow, slow slip events that occur at depths and pressures where the Cascadia ETS cycle would not be expected, suggesting that the frictional and fluid properties of the Hikurangi interface differ in important ways from the better studied Cascadia system. Geodetic data from the GeoNet network in New Zealand shows interseismic coupling that is spatially variable, with some portions of the interface apparently fully locked and accumulating elastic strain, and other portions showing partial coupling or creep. The paleoseismic record of Great Hikurangi ruptures is incomplete, partly because the relevant coastal deposits are less well studied than those of Cascadia, and partly because the geometry of the subduction zone makes some proxies for past ruptures harder to read. But the pattern of migration matters beyond what it tells us about imminent hazard, because it tells us something more fundamental about the connectivity of the fault system. Systems that show lateral migration after large events are systems in which segments communicate. The mechanical communication between fault segments through static stress transfer, through dynamic stress changes from passing seismic waves, through fluid pressure changes driven by poroelastic effects in the crust, is a characteristic of fault systems that have developed a degree of geometric and mechanical continuity along their length. Isolated fault segments separated by large geometric discontinuities, changes in strike, changes in dip, major structural barriers, do not show this kind of coherent lateral propagation. The fact that communication is occurring in the Kermadec Tonga system means that this is not a collection of independent faults that happen to occupy the same geographic region. It is a connected system in which the state of one segment genuinely influences the mechanical state of its neighbours, and that has implications for long-term hazard assessment that extend well beyond the current sequence and the current week. The Cascadia system is showing elevated ETS activity during a period of extended strain accumulation. The 791 tremor events in a single day represent an unusually dense clustering within a process that is itself a normal part of the Cascadia loading cycle. The ETS cycle has been systematically observed for roughly 2 decades since its discovery, and during that time it has shown considerable variability in amplitude, duration, spatial extent, and temporal clustering. The northern Cascadia segment, roughly the portion offshore of Vancouver Island and the northern Washington coast, shows cycles of roughly 14 months between major ETS episodes. The southern Cascadia segment shows less regular behaviour, with a somewhat shorter recurrence interval and less spatial coherence. Individual ETS episodes within a given cycle can vary dramatically in tremor productivity. Some cycles are characterized by a single prolonged burst of tremor propagating smoothly along strike over several weeks. Others break into multiple shorter episodes that cluster and then quiet down and then resume. The factors controlling this variability are not fully understood, though current models suggest a role for heterogeneity in the frictional properties of the transition zone interface, and for variability in the flux of fluids released from the subducting slab. A single day of high activity does not, by itself, indicate a change in the state of the locked zone above. It is a data point in an ongoing process, but the ongoing process is itself significant because of the context in which it is occurring. Cascadia has been accumulating strain since 1700. 326 years of continuous plate convergence at roughly 3 to 4 centimeters per year translates to more than 10 meters of potential slip accumulated on the locked interface. To put that number in physical terms, when the Cascadia megathrust eventually ruptures, the two sides of the fault will move past each other by 10 meters or more in the space of 3 to 5 minutes. The ground will shake at accelerations that will exceed the structural capacity of unreinforced masonry buildings across a region stretching from northern California to southern British Columbia. The rupture will propagate along the full length of the fault, approximately 1,000 kilometers, in a process that will take 2 to 3 minutes from initiation to completion, generating seismic waves that will radiate outward through the continent and simultaneously deforming the seafloor above the rupture zone in a way that will launch a tsunami. The ETS cycle does not tell us when this will happen, but it tells us that the loading mechanism is active, that stress is being transferred into the locked zone from below, cycle after cycle, adding to the stress being transferred from the sides by continuous plate convergence. That the system is not dormant, not quiescent, not on pause in any meaningful mechanical sense. It is doing what subduction zones do between great earthquakes. The intervals between great Cascadia ruptures, stretching from 1 or 2 centuries to more than 5, are not periods of rest. They are periods of accumulation. Every year of that interval, the locked zone stores more elastic strain. Every ETS cycle, the transition zone transfers a small additional increment of stress to the locked zone from below. The interval feels like waiting. The physics is loading. So here is the honest assessment, stated as plainly as the evidence allows. 2 megathrust systems are showing internal stress signals. Both signals are consistent with normal tectonic processes operating within the expected range of behavior for their respective fault types. Neither signal constitutes evidence of imminent rupture on any specific timescale. No accepted geophysical mechanism connects the two systems in a way that would make the activity of one physically relevant to the timing of the other. The temporal coincidence of their current activity may reflect nothing more than the statistical clustering that characterizes earthquake occurrence at all scales, from individual aftershock sequences to the apparent burstiness of global seismicity over periods of months to years. And none of that is reassuring. It is not reassuring because the absence of evidence for imminent rupture is not evidence of absence of hazard. These are different claims that are frequently conflated in public discussion of seismic risk, and the conflation is dangerous. We cannot say that rupture is imminent because we lack the mechanistic understanding and observational precision to make that determination. But we also cannot say that the hazard is low because the physical basis for high hazard is well established, thoroughly documented, and entirely unaffected by what the tremor count was on any particular day. The hazard for Cascadia is not elevated this week because the ETS count spiked. The hazard for Cascadia has been elevated and building for 3 centuries. The ETS spike is not creating the hazard. It is a signal emitted by a process that is contributing to a hazard that already exists at a level that demands serious societal attention. The Kermadec system is legitimately redistributing stress along a corridor that terminates at a megathrust margin, capable of generating an earthquake and tsunami that would devastate coastal New Zealand and send waves across the southwest Pacific. The Cascadia system is legitimately in a loading phase that has persisted since the last rupture in 1700, and will end, eventually and with physical certainty, in a catastrophic earthquake. Neither of these statements requires the two systems to be connected to each other. Neither requires a geomagnetic trigger. Neither requires a global pattern or a synchronized ring of fire. Each stands on its own as a statement about a single fault system doing what fault systems do, accumulating toward failure on a timescale that is geologically brief and humanly unknowable. The human desire to connect these signals into a unified narrative is understandable and needs no apology. We are pattern-recognizing organisms shaped by millions of years of evolution to find causal structure in environmental signals, to build predictive models from limited data, to err on the side of detecting threats that may not be there rather than missing threats that are. These cognitive tendencies are not flaws, they are why we are here, but they operate at a scale and speed calibrated to the threats of the Pleistocene, not to the geological timescales of tectonic hazard. When two dangerous systems show unusual behaviour at the same time, we want the coincidence to mean something, because a meaningful coincidence can be analysed and perhaps prepared for. A meaningless coincidence offers no such comfort. It just means that the world contains multiple independent threats that do not coordinate their schedules for our convenience, and that we must assess and prepare for each of them on its own merits, without the false reassurance of a unified narrative that would make the whole situation feel more tractable than it is. But even coincidences without shared cause can serve a useful purpose if they redirect attention toward things that independently deserve it. The Kermadec migration deserves monitoring attention because it tells us something real and currently unfolding about the mechanical state of a connected fault system that includes some of the most important subduction hazards in the Southern Hemisphere. The Cascadia ETS cycle deserves monitoring attention because it is the visible expression of a loading process that is building toward an outcome that the geological record has demonstrated multiple times, that probabilistic hazard models have characterized extensively, and that emergency planners in 3 Pacific Northwest states and 2 Canadian provinces have spent decades trying to prepare populations for without fully succeeding. These are not emergencies in the sense of acute crises requiring immediate protective action. They are not predictions. But they are reminders, and reminders of this kind have value precisely because the human attention span is poorly matched to the timescale of the hazard. The great earthquake that Cascadia will eventually produce is not an abstraction or a theoretical possibility. It is a physical certainty established by 3 centuries of loading and 10,000 years of geological evidence. The difficulty is that its certainty is coupled to profound uncertainty about timing, and that coupling creates a situation in which the certain eventual outcome is psychologically managed through indefinite deferral. The earthquake will happen, but not today, not this year, maybe not in our lifetimes, and so the preparations that would be made if the timing were known remain perpetually incomplete. The Earth does not issue warnings the way we wish it would. It does not build in a linear sequence from green to yellow to red, with clear threshold crossings that a monitoring system can detect and translate into actionable alerts. It operates through continuous processes that produce intermittent signals, and the relationship between those signals and the ultimate events they may precede is probabilistic, ambiguous, and often unresolvable until the event itself provides the retrospective frame that makes the preceding signals legible as precursors. The seismologists who monitor the Kermadec Trench are not waiting for a predicted earthquake. They are watching a stress field evolve in real time, documenting its spatial and temporal pattern, comparing it against the known behaviour of analogous systems, in which similar migration sequences have preceded significant ruptures, and updating their understanding of how mechanically connected fault systems redistribute energy and hazard after large events. The goal is not prediction, the goal is characterization, understanding the system well enough that if something significant does follow from this sequence, the scientific community will be better positioned to understand why and to refine the models that inform future hazard assessment. The seismologists who monitor Cascadia are engaged in the same fundamentally open-ended process. They are not counting down to a great earthquake. They are tracking the loading cycle with the best available tools, measuring the tremor, characterizing the spatial and temporal patterns of ETS behavior, deploying offshore geodetic instruments on the seafloor above the locked zone to try to improve the resolution of interseismic coupling models, and running forward simulations of rupture scenarios to provide the ground motion and tsunami inundation models that emergency managers need to plan evacuation routes and shelter locations. The monitoring is not passive observation, it is active scientific engagement with a hazard that is as well characterized in its physics as it is poorly constrained in its timing. None of this is dramatic in the way that the topic might seem to demand. None of it makes for easy headlines. The reality of how earthquake science operates, how it monitors, models, updates, refines, and communicates about geological hazards is genuinely unglamorous. It is painstaking work conducted by people who are professionally fluent in uncertainty, who write papers that say things like the results suggest an elevated but not conclusive probability, and who have learned from painful experience that the distance between a scientifically defensible statement and a publicly actionable warning is often vast and treacherous. The migrating swarm is not heading toward New Zealand with inevitable destructive intent, marching southward on a schedule that an alert system could track and a population could evacuate ahead of. The Cascadia tremor spike is not the final warning before the big one, a seismological klaxon announcing that the window of preparation has closed. The geomagnetic storm is not pushing faults to failure from space, adding cosmic urgency to terrestrial processes that operate on their own sufficient tectonic logic. The Ring of Fire is not synchronized in a global pattern of coordinated seismicity that signals an imminent reorganization of the Pacific Basin. These narratives are available and circulating. They are not supported by the evidence. But two of the most dangerous subduction systems on Earth are showing the same category of behavior at the same time. Both are redistributing stress, one laterally through static Coulomb transfer along a connected arc system, one vertically through episodic tremor and slip loading the base of a locked megathrust interface. Both on faults capable of producing the kind of earthquakes that reshape coastlines, rewrite maps, and end the ordinary lives of hundreds of thousands of people without warning. The question that everyone wants answered is whether this means something is about to happen. And the honest answer is that we do not know, and anyone who tells you they do is either mistaken about the current state of earthquake science or unconcerned about the consequences of overstating what the evidence supports. What we do know is that these systems are active, that they are doing what subduction zones do between great earthquakes, that the signals they are producing are real, measurable, scientifically significant, and consistent with ongoing tectonic loading that has been underway for much longer than any of the signals we are currently observing, and that the great earthquakes these systems will eventually produce are not possibilities to be weighed against the possibility that they will not occur. They are certainties, physical certainties. The only unknown is when, and that is the part that keeps the people who study these systems watching their screens through the night. Not because they expect to see a definitive answer today, or this week, or perhaps in their careers, but because the faults do not announce their intentions in advance. They do not accelerate gradually toward a clear threshold that instruments can bracket and warn systems can relay. They operate in apparent stability for decades or centuries, producing signals that look exactly like the ones we're seeing right now, until one moment, without the additional warning that everyone hopes will be there. The accumulated strain exceeds the frictional strength of the locked interface, and the fault moves. When that moment comes for Cascadia, the ground from Northern California to British Columbia will shake for 3 to 5 minutes. Not the brief sharp shaking of a moderate earthquake that people in the region have experienced before, the 10 or 15-second jolts from crustal events, or deep intraslab earthquakes that rattle windows and knock items off shelves and then stop. 3 to 5 minutes of sustained, building, violent shaking from a rupture propagating along 1,000 kilometers of fault. Long enough that people who initially stand up to brace themselves will have time to realize in the continuation of the shaking that this is different. Long enough that the character of the motion will change as different phases of seismic energy arrive. Long enough that structures that might survive a shorter event will accumulate damage beyond the point of recovery and begin to fail. A tsunami will be generated within seconds of the initial rupture, the seafloor above the locked zone rebounding upward as centuries of elastic strain are released, displacing the entire water column above it. Coastal communities will have 15 to 30 minutes before the first wave arrives. In some locations, the shaking itself will generate a local tsunami from submarine landslides triggered by the ground motion, potentially arriving even faster. The wave will not look like what most people picture when they hear the word tsunami. It will not be a single towering wall of water cresting cleanly above the shoreline. It will arrive as a rapid rise of water, a surge, filling harbours and estuaries from below, overwhelming seawalls, moving inland with a speed and depth and force that individual human bodies cannot resist. It will recede and return multiple times, with successive waves potentially larger than the first, over a period of hours. Infrastructure will fail on a regional scale. The Cascadia subduction zone runs beneath the most seismically vulnerable built environment in North America outside of the San Francisco Bay Area. Portland sits on a mix of soil types, much of it liquefiable fill along the Willamette River corridor that will undergo severe ground deformation during sustained shaking. Seattle's buildings include thousands of unreinforced masonry structures and older soft-story wood frame apartments that have been identified as high-priority collapse risks in major earthquakes, but whose retrofit programs have proceeded slowly against the weight of cost and political inertia. The transportation network, including the bridges across the Columbia River that are critical to post-earthquake emergency response and supply chain restoration, will be severely disrupted. Water and wastewater systems will fail across the region. Power will be out for weeks to months in the most affected areas. And the question that people will ask in the aftermath, the question that always gets asked in the aftermath of major seismic disasters in places that knew the risk existed, will be whether there were warning signs. The answer, almost certainly, will be yes. There were always warning signs, the ETS cycles continuing through the years before the event. The tremor spikes that made scientists note the system's activity, the loading signals visible in geodetic data, the probabilistic hazard models that place Cascadia firmly in the category of faults overdue by some recurrence metrics, the geological evidence of past ruptures preserved in coastal sediments and ghost forests and deep ocean turbidite deposits, the oral histories of indigenous communities that remembered what the last one did. All of it was there, documented, published, presented at conferences, reported in newspapers, incorporated into emergency planning documents. The warning signs for Cascadia have been visible in the form of the geological and monitoring record, for 20 years of systematic observation and for thousands of years of geological time. They just do not come with a date attached. When that day comes for the Hikurangi margin, or for whatever segment of the Kermadec Tonga system finally reaches its failure threshold, the same retrospective illumination will occur. The migrating swarm from this period will be re-examined in light of what followed. The Coulomb stress transfer calculations will be rerun with better constrained source models, the stress changes mapped onto the receiving faults with the precision that post-event data allows. The geodetic record of the months preceding the rupture will be analysed for any slow slip or surface deformation anomaly that, in real time, was too subtle to distinguish from noise, but that in retrospect, given the known rupture location and mechanism, might contain a recoverable signal. And someone will point to this period, to the southward stepping events following the Tonga 7.5, and say that the system was telling us something. It was, it is. Both systems are telling us something right now. The Kermadec Trench is telling us that stress from a major earthquake is propagating through a mechanically connected fault system in the direction of a megathrust margin that has its own substantial loading history and its own eventual rupture waiting in the geological future. Cascadia is telling us that the loading cycle continues without pause, that the locked zone is absorbing another increment of strain from another ETS episode, in a series that stretches back decades, that the clock whose last reset was January 26, 1700 is still running. Neither system is telling us when. The when is the information we most want, and the information that the physics of these systems most resolutely withholds. It is embedded somewhere in the distribution of stresses across a locked interface that no instrument can directly sample, in the heterogeneous frictional properties of a fault zone buried beneath tens of kilometers of rock, in the precise location of the first small patch of interface that will reach its local failure stress and begin the rupture nucleation that then propagates to encompass the whole. These quantities are not hidden from us by insufficient effort or inadequate funding or want of scientific ingenuity. They are hidden from us by the geometry of the Earth, which places the critical zone below the reach of any borehole, beneath the resolution of any remote sensing system, behind a veil of material that transforms any surface signal into the smeared, attenuated, ambiguous thing that arrives at our seismometers and GPS receivers. But here is what I want to leave you with, because this is the thought that sits at the centre of everything we have discussed and everything that these two systems represent about the relationship between human civilization and the planet it occupies. The Earth is not waiting. We are. The tectonic forces driving these systems operate continuously, relentlessly, without pause and without regard for human awareness or human schedules. The plates converge at their geologically determined rates, a few centimetres per year, indifferent to the civilizations built above them. The strain accumulates in the locked zones with the mechanical precision of a spring being compressed by a force that does not tire and does not stop, the faults load, the locked zones hold, the ETS cycles pulse, and the signals we detect are not warnings issued by a planet trying to communicate with us. They are observations of a physical process that is happening whether we observe it or not, that was happening before we had instruments to detect it, and that will continue happening long after any particular generation of scientists and monitoring networks has been replaced. What we bring to this process is awareness. The awareness that the process is occurring, the awareness of what it will eventually produce, the awareness of what the geological record shows has happened before and will happen again. And from that awareness, the possibility of preparation, of building codes that account for the shaking levels these faults will generate, of tsunami evacuation routes that give coastal populations a real chance of reaching high ground in the time available, of emergency response systems that have thought through the post-earthquake logistics of a region where bridges have failed and power is out and communications are down across an area larger than many countries. The Kermadec migration may end quietly, the stress dissipating through a continuing series of moderate events that rearrange the regional stress field without accumulating sufficient load on any single segment to drive a great rupture. This outcome has precedent. Many stress migration sequences in subduction systems resolve through distributed moderate seismicity, rather than through a single large event. The stress gets used up, distributed across the fault system in small increments, and the migration pattern gradually loses coherence as the driving stress perturbation from the main shock is accommodated. It may be happening now. We will not know it has happened until the sequence ends and the catalogues examined retrospectively. Or the migration may be the early expression of a cascading stress transfer sequence that eventually loads a critical segment past its threshold. That outcome also has precedent. The Tohoku earthquake of 2011 was preceded by a series of large earthquakes in the months and years before the main rupture that some researchers now interpret as stress transfer events that progressively loaded the eventual main shock segment. Whether the Kermadec Tonga sequence represents the first category of outcome or the second is not determinable from current data. The Cascadia ETS spike may be an unremarkable fluctuation in a process that continues for another 50 years, another century before the locked zone finally fails. The variance in ETS behaviour is high enough that a 791 event day, notable in the context of the observed record, remains within the range of behaviour the system has shown during periods that preceded nothing. Or it may be the latest in a long series of loading pulses that has finally brought the accumulated strain close enough to the failure threshold that the next significant external perturbation, tidal, seismic, fluid-driven or otherwise, will be the one that initiates nucleation. We do not get to know which scenario we are in until the scenario resolves. That uncertainty is not a failure of science. It is the fundamental nature of the systems we are studying, systems that operate in a parameter regime where predictability is limited by irreducible physical constraints. Accepting that limitation while continuing to do the best science possible within it is not resignation. It is the only honest posture available to people who take these systems seriously. The swarm is still migrating south along the Kermadec arc, its energy decreasing with each step but its trajectory uninterrupted. The tremor is still cycling through the Cascadia transition zone, the slow slip events propagating along strike, loading the locked zone above with each passage. The locked zones are still holding the strain of decades and centuries, as they have held it without visible change since the last time each of them failed. For now, they hold. They have held through hundreds of ETS cycles. They have held through regional earthquakes and distant great earthquakes, and the continuous background noise of a planet that is never truly still. They hold because the frictional strength of the interface still exceeds the accumulated stress trying to drive it to failure. The margin by which they hold is the number we cannot measure, and that margin, whatever it is getting smaller, not this week specifically. Not because of the tremor spike or the migrating swarm or the geomagnetic storm, but because the plates have not stopped moving. Because the strain has not stopped accumulating. Because the process that loaded these faults to their current state is the same process that will eventually load them past it. The Earth is not waiting. We are. And the distance between the state these faults are in now and the state they will be in when they finally fail is not a distance measured in any unit that human impatience can track or human instruments can resolve. It is measured in the slow, certain arithmetic of accumulated strain, and it is, without question, still counting.